Welcome to the next lecture of cellular system. In today's lecture, we will try to quantify some important quantities. In last lecture, what we studied is, suppose you have a base station here, let's call it A, which uses some set of frequencies. Then we will have adjacent base stations B, C, D, E, F and G. Okay, so if all of them use different frequencies, and then we reuse the frequencies. Okay, so now afterwards, suppose here I will repeat pattern here B, and here I can put G, C, okay, D, and here again A, B, and here again G, F and E. Okay, so I have just plotted here, drawn here 2. So I will now demark so this is one such a group. So this one group is called a cluster. Okay, so what means a cluster? That in cluster there, how many cells are there? Here it is 7. It can be more than 7 also. In previous lecture we had 3 also in this cluster. It means that all of them will use different frequencies. In fact, if we are given a particular number of frequencies, they will utilize all the frequencies. Then we have the next group, next cluster. So this cluster will reuse all the frequencies. Okay, now let as denoted by X, the S denotes the total number of full duplex channels available for use. One important thing I would like to tell you is that in wireless communication, especially mobile communication jargon, when we say a channel, it means transmitter and receiver communicating at particular frequency. Okay, so if I am allocating a channel F1 to a particular user, so that particular user is communicating with base station using frequency F1, and then user 2 is communicating with the base station using frequency F2. We will call these two are 2 channels. This is the jargon you have to get used. And what does full duplex channel mean? So duplex means that, see, we have to communicate from mobile to base station as well as from base station to mobile. So 2 frequencies will be allocated. One for uplink, we call this uplink. Uplink means from mobile to base station, and one for downlink. from base station to mobile. So S is now the total number of channels. Actually, it means total number of frequencies available. Okay. Now each cell, now let is denoted by small k. What is the small k? So each cell, it is a number that each cell is allocated k channels. Definitely k has to be less than S. And how many? So now there are, let n be the number of cells. Let n is equal to number of cells in a cluster. Okay, now you know what cluster is in a cluster. Okay, then how can we relate this S and N? It will be definitely k times n. Let's come to this point, this figure. So suppose if you take example of the above cluster, take cell B. So cell B is given k channels. Okay, similarly cell G will also be allocated k channels. Now channels, actually we are giving them the pair of frequencies. Similarly k channels here, n is 7. So S, the total number of full duplex channels, will be k times n, which will be 7 times k. Now suppose if k is equal to 50, as an example, that each cell is given 50 different channels. What it means that each cell can serve at a time 50 different mobile users. Then this S will be 350. Okay, so there are total of 350 channels available. That is 3 different frequency pairs which are available total, and all in one cluster they will use all these 350. So the k channels given to B will be different from G, then F will be given different channels, A will be given different channels, C will be given different channels, D and E different channels. But in next cluster, the channels which B will use here will be same as the channels which B uses here. Since they are far away, so they will not receive each other's signal significantly, so there will be very less interference. It will not be zero at all, because wireless signals ideally can get transmitted in the whole space, but the signal strength will be very less. Now if cluster is replicated m times, so if cluster is replicated m times, what does that mean? So here I have drawn two clusters. Suppose a full Srinagar area has maybe 100 such clusters, then m is equal to 100 for that particular area. That is what it means. So in a particular area, how many such clusters are there? That will be denoted by m. Then we can have a measure of we can see a capacity of this cellular system as total number of full duplex channels, and that will be called C, and that will be definitely m times S or m times Kn. We note down one important relationship, that this S is equal to Kn or K is equal to S by N, right? See, if N is increased, N is more, then for a fixed S, we have less number of channels allocated to a particular given cell. So hence this 1 by n has very important impact on how many channels will be allocated. It is also called frequency reuse factor. Frequency reuse factor. So we would like this frequency reuse factor to be as large as possible because we want to save spectrum, which means n should be as small as possible, right? So from design point of view, we would like to have smallest n possible. But at the same time, suppose if you, what are the possible values of n? So n cannot take any arbitrary value, as you can see from this figure. Here n is equal to 7. One more possibility is smaller number is n is equal to 4, which we have done previously. So here is A, here is B, here is C, and here is D. Okay, now after this I will repeat the pattern. So I can put here possibly D is farther away, and I can put here B, and I can put here C, right? And then I can put here A, and again here C, right? So you can see that we have one cluster here, and we have another cluster here, and then this will form one more cluster. Okay, but if you take 5, then you will see that we will not get equidistant cells. So what I mean is that the cells which use the same frequency, they should be at equal distance from each other. So n takes a particular values. In fact, we will I will share a separate video for its proof, or maybe some notes. But n takes values of this form: I square plus ij plus j square. Rappaport doesn't have proof for this. I will show it separately, where I and j are integers. That is, the possible values of n are, you have to give different integer values to I and j, of course positive. Okay, and you will get different possible number of cells in a cluster. And they have a special meaning also. Suppose if I write I is equal to 1, j is equal to 1, then I will get n is equal to 3. 3 is also one possible number. We have done 3 actually previously. Today we did for 4. Similarly, if I write I is equal to 1, j is equal to 2, so I will get n is equal to 1 plus 2 plus 2, so 5. Okay, yeah, so I think this that is why this 4 I think is not correct. Yeah, because we will not get all the equidistant clusters. Okay, so there will be, and the shape is also not symmetric. So n is equal to 5. We will have to actually put here one more e. Anyways, similarly, if you put I is equal to 2, j is equal to 2, we will get n is equal to 4 plus 4 plus 4, which is 12. Okay, and if I put I is equal to 1, j is equal to So this is square 4 plus 3 is 9, suppose 3. So another possible value is I is equal to 1 plus 3 plus 9, which is 13. Oh, we can actually put 0 also. That is how we will get 4. Yeah, just see. I is equal to 0, j is equal to 2, we will get n is equal to 4. Yeah. So 4 is also correct. Okay. But I haven't drawn it properly. Maybe we will have to check it because they should be of the same shape. I is equal to 0 and j is equal to suppose 3 or maybe 2, then n is equal to 0 plus 0 plus, okay, that I have to write. So I is equal to 0, j is equal to 3. This will give us n is equal to 0 plus 0 and plus 9. Oh, here I have I is equal to 1, j is equal to 2. So this will be 1 square into 2, 2 square. That will be 7. Sorry. Okay. So these are the possible different values which n can take. Now I will give an example, a practical example with some real value of frequencies to have some hands-on computation for the cells. Is an example. Okay, suppose you have a total bandwidth is, which you can use, 33 megahertz. Okay, so let me tell you that what does it mean. It means that suppose you may have 900 megahertz as the starting frequency, then you can use frequencies up to 933 megahertz. That is what bandwidth means. Okay, this is as an example. It can be anything. It can be 1 gigahertz to 1.33 gigahertz. Okay, this also has bandwidth same, and is allocated to something called frequency division duplexing, FDD, frequency division duplexing cellular system. What does it mean, FDD? See, in telephone or in mobile, the transmitter and receiver, first you see radio broadcasting. In radio broadcasting, there's a transmitting tower and there's the radio receiver. There's always one way communication. We call that half duplex. Oh, not even half duplex. That is even very simple. There you don't have to communicate anything from the radio at all. That is the simplex communication. Simplex or one way. So this is radio. Then the other, if you remember, there were earlier those walkie-talkies. What they used to do is when one person is speaking, other is not able to speak, and when other is speaking, the first person is not able to speak. So that is called half duplex. In half duplex, we do something called time division duplexing. What we do is, suppose we have this time frame and there's a transmitter and receiver. So in time frame 1, transmitter can only communicate. In time frame 2, the receiver can communicate back. Then again transmitter can communicate. Then again receiver can communicate, so on and so forth. So in this way, both transmitter and receiver, they are communicating, but they are not communicating simultaneously. But the better is that transmitter is given two frequencies, F1 and F2. Receiver is here. They are given these two frequencies. So this transmitter will use F1 to communicate from when when the transmitter wants to transmit to receiver, and F2 will be used when the receiver wants to communicate to the transmitter. And this can be done simultaneously since they are communicating at different frequencies, so they can do it simultaneously without interference. This is called frequency division duplexing. So now in this system, the example which I am giving, we have 33 megahertz bandwidth. It is allocated to a particular frequency division duplexing system. Okay, that is, it will use two simplex channels. See this, if you have only one frequency, right? Suppose you have only F1 frequency, then it is a simplex system. If you have only F2 frequency, then it is a simplex system. So these are the two simplex systems. So F1 only is one simplex system. F2 only, it is again one more simplex system, right? These two together, when we use both F1 and F2, they form the duplex system. And suppose in this case, the simplex frequencies, they are having this 25 kilohertz simplex channels. Okay, both. So this together provides full duplex channel, full duplex communication. Okay, and these are used for different purposes. So there is they can be used for voice, to carry voice message from one mobile to base station, or base station wants to send other signals, it can be used for that also. Now let's assume that the reuse factor, or n, is having value 4. It means that 4 cells are using all the available bandwidth. Okay, and then it is repeated, then frequency is reused after 4 cells. Okay, now we need to compute number of channels available per cell, okay, for this system. First of all, you see that what is the bandwidth of full duplex channel. Simplex channel has bandwidth 25 kilohertz. 25 kilohertz bandwidth frequency is provided for simplex communication, that is, suppose from transmitter to receiver, similarly from receiver to transmitter. This is this for simplex channel. For duplex channel, when we use both the frequencies, what will be the channel bandwidth? Very simple, 2 into 25, right? 50 kilohertz per duplex channel. Okay, now you have 33 megahertz or 33,000 kilohertz total bandwidth, right? And divided by one full duplex channel uses 50 kilohertz bandwidth. So this will be the total available channels, total available number of channels. Okay, so this you compute, it will be 660 channels. Okay, it means actually that you have 660 full duplex channels. That is, each full duplex channel, actually for that you assign 2 frequencies, and those frequencies are allocated within a bandwidth of 25 kilohertz. Okay, now if n is 4, then how many channels are available per cell? See, now you have one cell, second, third, and fourth. See, all these four channels, they utilize 660. Sorry, all these four cells, one cluster, they utilize 660 channels. Now, how many channels are allocated to one cluster? So, total number of channels available per cell is 660 by 4, which is roughly 165 channels. Okay, that means if you keep n is equal to 4 for this system in one cell, that is in this one hexagonal area, 165 mobiles can communicate simultaneously with the base station because they all will be allocated different channels. What happens after 165 if suppose all the 165 people are communicating and after that you still try to communicate, then there will be something called call drop. Now suppose if we take n is equal to 7 as the reuse factor, then what will be this k, which is the total number of channels available per cell? It will be 660 by 7, which is 95 channels. See, I will explain one trade-off here. You can take n is equal to 12. We don't go beyond 7 is best, okay, and 12 is very rare. Then it is 660 by 12, around 55 channels. See, why we would like to increase n? Suppose with 4n you may feel the interference when frequency is reused in nearest this co-channel. You will feel interference, more interference there. Then you increase n, but there is a trade-off. As you increase n to decrease the interference, then you get less number of channels per cell. So while designing a mobile communication system, we have to take care of these trade-offs more often. Okay. So in next lecture we will study how to assign the channels, and also what if mobile moves from one base station to other base station. There is something called handoff strategy, and how to prioritize the handoff. Okay, so we will briefly do that also, and then finally I will, in this chapter we will be doing interference analysis. Okay, that will end the cellular system part, and then we will go for channel modeling, large scale as well as small scale channel modeling, couple of lectures before that also. Okay, thank you.